Okay, in section 6.2, we will be talking about volumes. So in trying to find the volume of a solid, we face the same type of problem as in finding areas. We have an intuitive idea of what volumes means, but we must make this idea precise by using calculus to give an exact definition of volume. We start with a simple type of solid called a cylinder, or more precisely a right cylinder, as you can see how this is illustrated here. And what you notice is that a cylinder is bounded by a plane region B1, which is the base here, called the base, and then you have a congruent region B2 in a parallel plane. The cylinder consists of all points on line segments that are perpendicular to the base and join B1 to B2. If the area of the base is A and the height of the cylinder, which is a distance from B1 to B2, is h, then the volume of the cylinder is defined as the following. V is equal to A times h. Now, in particular, if the base is a circle with radius r in this next figure, then the cylinder is a circular cylinder with a volume equal to pi r squared h. So the base is a circle, the area of a circle is pi r squared, and then you're multiplying it by the height h. And if the base is a rectangle with length L and width W, then the cylinder is a rectangular box, also called a rectangular parallelepiped, with a volume V is equal to L times W times H, which is length times width times the height. Now for a solid S that isn't a cylinder, we first cut S into pieces and approximate each piece by a cylinder. We estimate the volume of S by adding the volumes of the cylinders, and we arrive at the exact volume of S through a limiting process in which the number of pieces becomes large. So we start by intersecting S with a plane and obtaining a plane region that is called a cross section of S. We're going to let A of x be the area of the cross section of S in the plane PX perpendicular to the x-axis and passing through the point X, where X is in between A and B. So we're going to take a look at this figure 2, and what you want to do is you want to think of this solid, okay, that you're looking at. S, so think of you're slicing S with a knife through X, and then computing the area of this particular slice. The cross-sectional A of X will vary as X increases from A to B. Now, if we divide S into n slabs, meaning that you have a lot of these slices of equal width, delta X, by using the planes PX1, PX2, and so on, to slice the solid. So basically think of this as a loaf of bread and you're cutting this in slices. Now if we choose the sample points x subscript I asterisk and the interval xi minus 1 x subscript I, we can approximate the ith slab, the part of the S that lies between the planes, from px I minus 1 to px subscript I, by a cylinder with base area A x subscript I and the height delta x, which is in figure 3. So if you take a look here, what you've done is, imagine again this is your, on your right here, this is the figure and it's cut in cross sectionals. And you can see here you have a value of A that goes from x subscript 0 all the way to x subscript 7, which is the value of B. And then this is that piece that we did in the previous section, where you have this delta x, and now you're trying to find basically the area of this cross section. So the volume of this cylinder is A of x subscript I times delta x. So an approximation of our intuitive conception of the volume of the ith slab S subscript I is the following. So the volume of that surface is approximately A times A of x times delta x. And then since we're going to have a lot more cross-sectionals, then it becomes a Riemann sum. So adding the volumes of these slabs, we get an approximation of the total volume. So we would have an approximation going from I is equal to 1 to n of A of x times delta x. And again, this approximation appears to become better and better as n approaches infinity. And again, think of the slices as becoming thinner and thinner, and therefore we define the volume as the limit of these sums as n approaches infinity. But we recognize that the limit of Riemann sums as a definite integral, and so we have the following definition. The definition of volume. So let S be a solid that lies between x is equal to a and x equals b if the cross-sectional area of S in the plane px through x and perpendicular to the x-axis is a of x, where a is a continuous function, then the volume of S is the following. So again, the volume is going to then interpret as a limit as n approaches infinity. And the formula is going to equal the lower limit of a to b, a of x dx. Now, when we use the volume formula, it is important to remember that a of x is the area of a moving cross-section obtained by slicing through x perpendicular to the x-axis. And notice that for a cylinder, the cross-sectional area is constant. So a of x would equal a for all x. So our definition of volume gives the following. V is equal to a to b a dx, which is equal to a times b minus a. And this agrees with the formula where V is equal to a times h.